brief thoughts about tangent planes, and one cool example from the book, from a homework problem in the book. So we've seen one version of this. We'll eventually see three versions of this. One version of tangent planes is z equals f of x, y. That's one way a surface can arise. This is a surface as when it arises as a graph of a function of two variables. And so this is really important, that f is only a function of two variables, but by including both the output and the input, we put it into 3D, and we get some sort of surface. It's a special kind of surface because it has to be the graph of a function. So as the vertical line test, that every point in the plane has only at most one point over it. And we've seen that the linear approximation to f gives us the tangent plane. If it's at a point AB, for example, then it's that value plus x derivative times delta x, as otherwise I say, plus the y derivative at a comma b
times delta y, y minus b. Okay. So that's the partial derivatives come in as we would expect for any kind of tangent linear approximation kind of thing. And they come in as an analog of the tangent line to a graph in one dimension. So that's what we already have seen. But the new way is a little different, although it's closely related. This is a very special, as I said, graph is very special. In terms of the implicit-explicit distinction that is really, really important in this course, this is a very explicit way to describe a surface. If I give you x and y, then you get z, and we're done. We've got a point on the surface. And any x and y that's in the legal domain of this function gives me something. So this is very explicit, although I'll say a word about that in a minute, how it can also be thought of as an implicit. But what about an implicit description? Oops. There's an implicit description going on that often happens that we can connect to what we've been doing more recently. It's not the only kind of implicit description, but it's by far the most common implicit description of a function of a surface in three-dimensional space. I have some other function, let's call it big F, that has three input and one output. And so f of x, y, b, and we need to name output, we can name it w. Okay, seems kind of slanty, huh? There we go. Sorry about that. And what we do is we look at a level set, or it's going to be a level surface, because if I have 3 degrees of freedom, but then I put in one equation by setting some function of it to be constant, then it's going to be a surface. So that's much more flexible. So for example, a sphere is a great example of a level surface. That's where x squared plus y squared plus z squared, at least if the centers of the origin, it's going to be x squared plus y squared plus z squared equals some number, namely, let's say the radius is a, that's going to be a squared. Okay, and that doesn't have to satisfy the vertical line test. It's can be much more general. And so this is a nice kind of description of a surface. And we'd like to know, how do we figure out the tangent plane to an implicitly defined surface like that? For example, one of the things that can happen here is that tangent plane might end up being vertical, like perpendicular to the y-axis, for example. You can't have that for a nice tangent plane of a differentiable function. So that's where the gradient comes in. The key fact is that this function f has a gradient, and the gradient of f, the thing we know about the gradient is that it points in the direction of greatest increase of the function, and in particular it's perpendicular to any direction where the function doesn't change at all, or in other words, it's perpendicular to the level surface that goes through the point where you're evaluating the gradient. So right here, the gradient's going to go here. Right here, the gradient's going to go off here. And this is wonderful because not only are we getting some idea of
description of the level surface, and hence the tangent plane. If it's perpendicular to the level surface, then it really should be perpendicular to the tangent plane at that point. We're also actually getting exactly the description we like to have. We're going to have a point, that's the point of evaluation, and the normal vector. We can use the gradient as the normal vector. So we don't have to do any work. It's really great. So we get the formula that you see in the book, which is that the tangent plane at, now I think I've messed up my letters a little bit, come to think of it. Well, I'll switch to x naught, y naught, z naught. I probably should have done x naught, y naught instead of AB in the first example, but I like AB sometimes better. It's going to be, there's our point, then let's say the gradient, now this is where I want to use A, B, and C, of f, let's say that at x naught, y naught, z naught is equal to A, B, C. So A, B, and C are now going to be the components of the gradient. Sorry about the change in the letters. And so we're just going to get, in vector form, it's gradient of f at that point, dotted with r minus r naught is 0. That's the standard way to take a normal vector and a point and get the equation. And it's just going to be a x minus x naught plus b y minus y naught plus c z minus c naught equals 0. Now what are a, b, and c though? They're the partial derivatives. So they're f sub x times x minus x naught plus f sub y times y minus y naught. Ooh, I'm getting a little cavalier here. I'll fix it up in a second. If you really want it all decorated out, then we want to remind ourselves where we have to evaluate those gradient vectors. The thing about the gradient is it's a very neat object. It's our first, I've mentioned this before, it's our first example of what's called a vector field that is a vector attached to every point. So it's really, in its full form, it's take the x derivative at the point you care about times x minus x naught plus the y derivative times y minus y naught plus the z derivative at x naught y naught z naught times z minus z naught equals 0. It's really easy, you just plug in. Okay, and I'll do an example now. However, well, before I do the example, one thing. Compared to the graph example, I think the book mentions this, you can make the graph example into this kind of thing. You can just say, oh, let's put everything from z equals f of x, y, from that previous example, put everything on one side. Here's your function big F of x, y, z. A graph is a level set of a very specific kind of function, z minus a function of two variables. And it's a nice little, very simple exercise to discover that if you use this formula on this f built out of the little f, then you get the previous formula. What that says is that a graph, I was calling it an explicit description. It really is. It's as explicit as it gets, but you can also very easily put it into the implicit picture. It kind of sits halfway between the most implicit and the most explicit kinds of descriptions of the surface. We will see other descriptions later. Okay, so here's the book problem I promised. It's just a little bit more interesting than just calculate the tangent plane. It's, suppose we have this surface and this other surface. Think about that for a second, what that is while I'm writing this one. So, and a question could be, so what is the first surface? It's an ellipsoid.
And the second surface is a sphere, but it's shifted, so its center is not at the origin. And one question would be, where do these intersect? In general, they're going to intersect in some sort of curve, because two surfaces are going to intersect in a curve. That could be a very complicated question to describe that curve. But they actually sidestep that issue, and they say, the claim is that these guys intersect at 1, 1, 2. And that just means if you plug 1 into here, 1, 1, 2, you get 9. That's correct. You can check it. If you
plug 1, 1, 2 into all this, you get 0. So it's on both surfaces, and the claim is that they are tangent. These two surfaces are tangent, mutually tangent at 1, 1, 2. Okay. And and that's going to mean that they just are going to share normal vectors. Because what it really means is they should share their tangent planes. Let's just see if they share normal vectors. All that amounts to is calculating the normal vectors. So for the first one, the gradient of f, up to scale. They don't have to have the same rate of change. They just have to have the sort of the same direction of maximum change. That's scale. I know you can't read that. Okay, so gradient of f is 6x, 4y, 2z, and that's a 2z. And at this point, it's going to be 6, 4, 8, so 6, 4, 4. I'm sorry, getting a little distracted with the kids in the house. Let's say this guy is G, big G. Okay, that's a little more complicated. It's 2x minus 8, 2y minus 6, 2z minus 8, and at this point it's going to be 2 minus 8 is minus 6. Ooh, that's suggestive. 2 minus 6 is minus 4. Aha. And 4 minus 8 is minus 4. And so these guys are scalar multiples of each other. And so they share a tangent plane because, of course, the scale of the tangent vector, the normal vector, doesn't really matter. These are going to give the same equation since you're at the same point and normal vectors that are just a scalar multiple of each other. Pretty cool. And then this actually has a nice relationship to Lagrange multipliers, which we'll come to soon.